No, I do not. There we go, yes. Can you guys hear me now? Oh, it's so weird. I have no idea. There was no setting that was different, but whatever. We'll figure it out, make it work. Everybody can hear me? Good. All right. Yay. All right. Okay, so let's start again. Anyway, do you guys have any questions on the homework? We have a quiz today on Appendix A and Chapter 3.3. Remember, yesterday I posted our video from our class, and I also posted a video from my 8 o'clock class, which had asked different questions on the homework. So if you guys have questions, you guys can ask me right now for the homework. 3.3, number 16. Sure, let's take a look. Okay. Did we do this one yesterday? I think I did this one maybe in class the other day. I can't remember if I did this for our class, but I will do it. So chapter 3.3, question 16. All right, so we have, so we've got a box. Let me draw this here. It looks like, okay, so we have a box, and we're told a bunch of things. So here's our base, here's our width, and here's our height, which we're told is 3 times the width. And then we're given the volume is 12 cubic meters, which, by the way, is also equal to the base times the width times the height. Okay, so I'm going to use this, right, to help me solve for things. We're told that the cost for things is the base costs $12 per square meter, and the sides have a cost of $8 per square meter. Now, they don't tell me anything about the top, but they only give me a cost for the base. So I can only assume that either there's no top or the top is free. So I'm only worried about the cost for the base. Okay, so don't worry about that. We're told that we need to minimize the cost, right? Which means I need to be thinking about surface area, because that's going to be what's going to dictate my cost things, right? So that this is in meters squared, which is an area unit, right? So I need to be thinking about the area of the different sides, like the base and the sides of my box here, okay? But I'm going to use my volume, because we're fixing the volume and we want to minimize the surface area. We want to know like what dimensions of this are going to minimize surface area, because our cost is based on our surface area. So what I need to do is I've got my, let's write it down again. So I've got my volume is equal to base times width times height. Now we're told that the height is 3 times the width. So I'm going to start base times width times 3 times width. And then I'm going to, this is equal to 12. I want to get this whole thing that I'm doing my my cost, my surface area stuff in terms of one variable, right? I just want it to be in terms of the base or the width or something like that. So I need to solve, I'm going to exploit the fact that they gave me a fixed volume number, and I'm going to solve for my base. So base, and I'm doing that because I could have solved for the width and had everything in terms of the base, but then this is base times 3w squared, and if I solve for w, then I'm going to have like a square root in there, which, you know, whatever. I mean, you can do that if you want, but I'm going to make this just in terms of my base. So this is 12 divided by 3w squared, which is equal to 4w squared. That's our base. So remember that. And then our height is 3 times w. So now I'm dealing with things that are just in terms of w, okay, which is good. So I have to start thinking about the area of the sides, and the area of the base. So it's a rectangular box, right? And I've got a side, let's draw them out like in different colors. So I've got a side here and a side here whose area is base times height, right? So this is base times height. And I have 2 of them, right? And then I've got another one. I'll do this in a different color, green and green. I've got a side here and a side here, right? Whose area is width times height. And then width times height. And I've got two of those, right? So, and then we also have that base, right? So this is, let me write this out a little bit better. So this is going to be area of the sides. This is going to be base times height times 2 plus width times height times 2, right? So all I did was kind of write it in more mathy stuff than words. So I've got the area of the sides. Now I'm going to do the area of the base, which the area of the base is like this piece right here, this bottom, which is base times width, right? So the area of the base is going to be base times width. Okay, so now we've got the cost. Okay, cost is going to be different depending on whether we're dealing with a side or a base. And then I've got my different things here. So the first thing I want to do is I want to start replacing base and height with things that are in terms of W. And then I also want to start putting in my cost on things because my sides are going to be cheaper than my base, apparently. All right, so let's start adding things up. So let's see, area of the sides. So let's start adding things up. So I've got, let's do this. How am I going to think about it? Let's see, so this is going to be sides. Let's do sides again. I'm just trying to think about how I want to do this. So this is going to be base times 3W times 2 plus width times 3W times 2. And then I can substitute this in here for W over W squared. And then let's add in our total cost. Sorry. 12 times base times width plus 48 times base times width plus 48 width squared. And then we can start substituting in the bases here. So this is going to be 12 times 4 over W squared times W plus 48, 4 over W squared times W plus 48 W squared. So I started like putting in my cost for things. Okay, and I started putting in like the values for different stuff. Okay, so now this is going to be equal to 48 all over W plus 192 all over W plus, I'm skipping some algebra that you guys can go do that too. And this is our total cost as a function of W. Okay, I can add these up. This is 240 over W plus 48 W squared. Okay, so this is my cost function. Okay, this is the thing that I want to minimize. Okay, so what I'm going to do is let me switch papers. I need a bigger paper. So TC, total cost, as a function of W equals 240 over W plus 48 W squared. Okay, so this is the thing I need to minimize. So I have to take the derivative with respect to W. So remember, this is 1 over W. So when I take that derivative, I get minus 240 over W squared. And then this is 2 times 48. We set it equal to 0 and we solve for W. So there's some algebra involved here. Basically, we're looking at 240 over 96 equals W cubed. I take the cube root. And I get W is equal to approximately 1.357. I have to check if it's a minimum. You have to check. If you don't check if it's a minimum, then you're not going to get full credit because the whole thing is we're solving for a value, but we have to make sure, whoops, sorry, we have to make sure that that's actually a minimum. Okay, so I'm going to check to see if it's a minimum. So I've got, I'm going to do the second derivative test. It's up to you if you want to do the first derivative test or second derivative test. Just remember like how you do them. Okay, so I did the second derivative test. So I'm right here. Here's my first derivative. I'm going to take the derivative of that. So I'm going to get 240 over W cubed plus 96, right? If I plug in right? I get a positive number. Okay, when I do that, so positive number on my second derivative means it's concave up, right? Which means that we're dealing with a minimum at W equals 1.357. So if I make the width equal to 1.357, and we're in meters, 1.357 meters, then I'm going to minimize the surface area, which then minimizes the cost. Okay. So 34. Okay, so 34 is a similar type of problem. We can work through that too. Okay. So 34 says, scroll up. So this is chapter 3.3, question 34. So question 34 is a similar type of problem. Just a second here, get this centered. Okay, so we have a box with an open top. Okay, and we're told that we have 2,000 square centimeter is available. What is the max volume of the box? All right, so let's draw out what we have. So I've got and we're told this is an open top, so I'm going to draw it like that. Right, so this is our box with an open top. So we have a width and a length and a height. Okay, it helps to draw pictures so that you can keep track of what it is you're trying to do. Obviously, you know, I'm setting up these dimensions, you know, myself, but and we were told, I think, that width and length are the same, and then our volume is equal to width times length times height, which means because these are the same, this is width squared times the height is equal to the volume. So we're told centimeter squared. Watch what we have. This is our surface area. Okay, which means that I'm going to sum this up. This is going to be the area of the base. There's no top, right? It's just the area of the base plus the area of the sides is going to be equal to that. So I'm going to think about that. So the area of the base, so this length and width are equal to each other. So the base is going to be equal to width times width. So this is width squared, right? Plus my sides are going to look like this. I've got width times height, width times height, width times height, and width times height. It looks like I've got width times height times 4, width times height. And that's equal to 2,000. So a picture is going to help you a lot, right? Because you need, I'm going to need this equation, and I'm going to need this equation here, okay? So I'm going to take this equation and I'm going to solve for H. So H equals 2,000 minus W squared divided by 4W. So that gives me an H. So then my volume equation will just be in terms of W. So I'm going to plug that into our volume equation. Right, so everything is now going to be just in terms of W, right? So then we'll say volume equals, plugging it in, and then moving it around, let's see, W squared times. Right, and then I can distribute and then get, volume, that's a volume. Volume equals 500 W minus W cubed over 4. Right, so I distributed the W squared, and then I, distributed this 4W into both of those terms there. So I get a volume equation here. So my volume equation, that's the thing that we're trying to optimize. Right, they told us, they said, what's the max volume of the box? So they're giving us a clue, like what's the function that we're trying to do. So this is our function that we're trying to do. Okay, I had to be given something. I had to be given surface area or volume. Like the previous question that we worked on, they gave us the volume and we worked with surface area. Now they're giving us the surface area and we're working with the volume. So we're just, manipulating our geometry. Draw a picture, it's gonna help you. No one's gonna grade you based on your picture, but it's gonna help you visualize the equations that you need to do and how you're going to add things up. Otherwise, how else would I know that, oh, this is, you know, the area of my box and my sides and whatever. Okay, so I've got my volume equation, and then as a function of W. So now I'm going to take my derivative because I'm trying to optimize this. Volume prime equals, this is going to be equal to 500 minus 3/4 W squared. Okay, and then I need to set that equal to 0 and then solve for W. So I'm going to get 3/4 W squared equals 500, and then W equals 25.8198, and this is in centimeters. So be careful, right? I'm taking the square root. I would have a plus or minus. Now a negative width isn't going to make sense, right? So I'm only taking the positive answer of that. So I have to check if it's a max. Okay, so how do I check if it's a maximum? Well, you can do a first derivative test or second derivative test. Either way, I did the second derivative test. I thought it would be easier, right? Because this is just a quadratic. So I got, this was equal to minus 6/4 times W, right? And if I plug in minus 6/4 times 25.8198, it's negative. All right, we can see it's going to be negative, but it helps to actually do it. So it's negative. Negative means it's concave down, right? Like this, which means that we're dealing with W equals 25.8198 equals a max. Okay, you have to do the check. It's not enough to find, otherwise it's just a critical point. How do I know if it's a max or a min? Like if I did this and it came out to be a minimum, I'd say there's no solution, right? There's no way to actually make, to maximize this. But because it's concave down, I can show that it's actually a max. How's that? Any other questions on 3.3 or Appendix A? I have office hours today. You guys are welcome to come by. But I ask you not to come by if you've already started the quiz. That wouldn't be very fair. Okay, you guys all set? You can think about it and then let me know. We'll come back to it at the end of class today. We're going to be continuing on talking about chapter 3.5. So let me go back to great. Okay, so we are in chapter 3.5. This is L'Hopital's rule. Okay, so L'Hopital's rule is a way to evaluate the limit of a function, right? We have, you know, we've got a function, we've got a limit that's approaching some value, or we're going to learn today also infinity. If we have an indeterminate form, we can take the derivative of the top, the derivative of the bottom, and apply L'Hopital's and apply the limit again to see if it's still indeterminate. We can use this, right, because there's a relationship between our derivatives and our function, and that's what L'Hopital's rule is exploiting. Okay, so let's just check really quick here. So we've got example 6. I'm on my lecture examples for 3.5, which I'll scan in later. L'Hopital's rule, can it be applied to this function here? So as x goes to 1, x squared plus 1. So I'm just going to remember, we always have to check. We have to check to make sure that our function is an indeterminate form. Indeterminate form is like 0 over 0, infinity over 0, you know, 0 times infinity, whatever. All these things that where you're scratching your head going, well, is it 0 or is it infinity, or what is it? You know, what should I do? If you're wondering, then it's probably a good bet that it's an indeterminate form. So we just have to check. So if I evaluate my limit here, I get 1 squared plus 1 all over 2 times 1 plus 1, which gives me 2 all over 3, which doesn't look indeterminate. Not indeterminate. But let's say I'm really excited, I'm on an exam, I'm going really quick, and I'm thinking I can just do L'Hopital's rule because it'll make it more simple. So we're going to use L'Hopital's rule, and I'm going to write down incorrectly. We're going to apply it to something that's not indeterminate, and we'll see what we get, right? So let's do it. So limit as x goes to 1. I'm going to take the derivative of the top, 2x, all over the derivative of the bottom, 2, which is equal to the limit as x goes to 1 of x. And I apply that and I get 1. Uh-oh, 1 does not equal to 2/3. This is our correct answer, right? And we're getting an incorrect, an erroneous answer. We used L'Hopital's rule incorrectly. It's going to lead you down the garden path. You're going to think, I'm doing it correctly. I'm getting a number. It's a real number, you know, but if you didn't do the check first to make sure that your function was indeterminate form, then you're going to get an erroneous answer on your L'Hopital's rule. So be careful. Always check. Okay. L'Hopital's rule incorrectly, it will give erroneous answer, okay, which will be incorrect. Alrighty, so let's move on to other types of indeterminate forms so that you can take a look and see what these things look like. So let's go ahead. Remember, we always check. So I'm going to plug it in first. So the limit as x goes to 0, 1 over the sine of x, 1 over the sine of 0 minus 1 over 0. Whoops, I'm running into problems here. So this is 1 over 0 minus 1 over 0, which this is undefined minus undefined. We can be a stickler about it and say this is actually, you know, like infinity minus infinity, okay, because it's undefined. It's, you know, what's actually happening. We can say use infinity as our form here. So it's an indeterminate form, but it's in a funny form, right? We talked about indeterminate forms as being like infinity over infinity, but also if I'm dealing with infinity minus infinity, that's also an indeterminate form. So I'm going to use L'Hopital's rule because it's an indeterminate form. So I can use L'Hopital's. But the first thing that I need to do actually is I need to combine this into one function as a fraction. So I have to find a common denominator. And then I need to combine both terms into one. So I have to do that. So x, so sine of x and x sine of x is my common denominator. So that's going to give me the limit as x goes to 0. I'm going to get x minus the sine of x all over x times the sine of x. Okay, and let's just do another quick check. So I'm going to evaluate this again. So as x goes to 0, I'm going to get 0 minus 0, because sine of 0, all over 0 times 0. So we're dealing with 0 over 0. So this is still indeterminate, which is no surprise, right? I mean, all we did was rewrite the function. It's just, it looks now more like our classic 0 over 0 indeterminate form. So we're going to use L'Hopital's. By the way, you may be wondering why I'm writing all this stuff. I wanted to just plow right through and do it because in this class, as well as in Calculus 2 next semester, you need to show that it's indeterminate. It's 0 over 0, it's infinity over 0, it's infinity over infinity, whatever it is. You need to show it's indeterminate. You can even write indeterminate. And then you have to specify you're using L'Hopital's. You can like use LHOP, right? Shorthand notation for it, but you have to specify that you're using this tool to evaluate this limit, okay? You have to state why you're doing it, and you have to state what you're doing, okay? As you move beyond Calc 1 and Calc 2, you don't have to state all this stuff, you can just do it, okay? But right now, because we're teaching you this material, it's new, we're checking to see that you know these tools, so make sure that you're spelling out that you understand the conditions under which you have to use it and what you're doing to resolve this conflict. Okay, so let's go ahead and we're going to apply it. So I'm going to do L'Hopital's rule. So my limit as x goes to 0. So now I take the derivative of the top. That's going to be 1 minus cosine of x all over the denominator function, just this function on its own. I have to use the product rule in order to evaluate it. So I'm going to say the first times the derivative of the second plus the second times the derivative of the first, which is equal to 1. Okay, so now I'm going to evaluate this again, right? So this is as x goes to 0, this is going to be, let's see, 1 minus, so cosine of 0 is equal to 1. This is going to be 0 times 1 plus 0. So we're still dealing with a 0 over 0. So it's still indeterminate, right? Which means I can use L'Hopital's again. Okay, so I take the derivative of the top, I take the derivative of the bottom, and then we'll reevaluate. So the limit as x goes to 0, this is going to become minus times minus sine. So this is just the sine of x all over. I have to do product rule here, but this is just the plain cosine. So I have to do product rules. This is going to be first times the derivative of the second plus the second times the derivative of the first, okay, which is equal to 1. Okay, plus the derivative of the sine is cosine of x. Okay, so let's go ahead and reevaluate what we have here. So this is, as x goes to 0, sine of 0 is 0, all over, this is 0 times 0 plus 1 plus 1. So I'm dealing with a 0 over 2. All right, here comes a trick question. Is this indeterminate? 0 over 2 is equal to 0. It's totally fine. Let's write that in a different color. Not indeterminate. Okay, 0 over 2 is just a number. And even if it was 2 over 0, that's not indeterminate either. 2 over 0 is undefined. Our limit doesn't exist, right? 0 over 2 is equal to 0. 2 over 0 is undefined. Okay, 0 over 0 is indeterminate. Okay, all right. So you guys finish writing that down. Okay, I'll scan these in later. So let's see, we're dealing with some more tools in our toolkit for how we process this stuff. So I can have functions of the form. Remember we did this before, f of x raised to the g of x. We did this, right? I think, I don't even know if we had it on a quiz. It was definitely a homework problem. It was like x to the x, or x to the x squared plus 3, something like that, okay? It's a function raised to the function power, okay? Now be very careful. This is not the same thing as e to the x. E is just a number, right? I mean, it's a transcendental number, but it's a number, okay? This is a function raised to a function, okay? This can lead to indeterminate forms that look like this. I can get 0 raised to the 0 power. Well, is it 0 or is it 1? You know, which rule is going to win out? Okay, so if you're asking yourself that question, it's probably indeterminate. I can get 1 raised to the infinity power. Well, is it 1 or is it infinity? See, I'm asking myself a question, like I don't know how to evaluate it. I can get infinity raised to the 0 power. Well, is it 1 or is it infinity? See how you're asking yourself this question of how do I evaluate this limit? If you're asking yourself that question, it's a good chance that it's indeterminate. Okay, you can use L'Hopital's rule to process it. Okay, so how we deal with it is we're going to take the natural log and then we're going to exponentiate. Then we're going to do L'Hopital's. Okay, so ln of something, right? E to the ln of something is just that something. So all we're doing is we're exploiting this inverse relationship between natural log and e to the x to help us, you know, essentially resolve this limit, okay? We'll do example 8 is a perfect example of this, okay? So example 8, okay, we're gonna take a look. Is this in? Made it worse. All right, let's see if I can get that. There, a little bit sharper. Okay, so limit of x raised to the x power. Now, if I just go to evaluate this, let's do our quick check, right? So this is going to be 0 to the 0. That was one of our indeterminate forms, right? So this is indeterminate. So I get to do L'Hopital's, but if I just jump right in and do L'Hopital's, it's going to be a mess when I go to take that derivative, right? Because it's supposed to be How am I going to do that? So let's think, right? So what I need to do is first I have to rewrite this, okay? So I'm going to think about doing a little bit of background work. So I'm going to compute the limit as x goes to 0 of the natural log of x to the x. Okay, natural log of x to the x. Remember we did this, limit as x goes to 0 of x ln of x. I think this was, yes, this is example 4. We did this yesterday, right? So example 4, we did x ln of x and we showed that it was equal to 0, okay? We happen to have done it already, okay? If we hadn't already done this, I'd need to do it now and evaluate what it is, okay? So this is equal to 0, and I'll write this is from example 4. We already did it, so I'm not going to go through the whole work on it again. So you can see the work from there. If we hadn't already done it, you'd need to go through and actually process it. All right, so the limit as x goes to 0 of x ln of x is equal to 0. Okay, I'm going to exploit that now. Watch. So I'm going to say this. So since my function f of x equals e to the x is continuous, we can exponentiate. Exponentiate means I'm going to make it into an exponent. I can exponentiate our result to get the desired limit. Okay, so watch what we're going to do. I'm going to say this. The limit as x goes to 0 from the right of x to the x is equal to the limit as x goes to 0 e to the ln of x to the x. Right, remember e to the x and ln of x are inverse relationships. So that means e to the ln of something is equal to that something. That's exactly what we've written here, okay? So what I'm going to do is I'm going to write this as, we know e is just a number, and we already did this work here. So this is e raised to the limit. This is where all the meat is happening. The limit of ln of x to the x, right? We just did this right here. And we said that was equal to 0. That was equal to 0. So this is equal to e to the 0. Because I evaluated that limit already. And e to the 0 is just equal to 1. Okay, this is a tool, right? It's a tool in your toolkit for evaluating a function like this. The tool is I take the natural log, because I'm going to get that function out of the exponent, and then I'm going to process this limit here. Okay, remember how we did that in example 4. Okay, I'm going to process this limit, I'm going to get some number. Now this works because this is equal to something. If this limit was undefined, I would have a harder time actually working through this. Okay, so if this limit is equal to a real number, I can exponentiate it, right? And then basically plug in that value for my e to the x, whatever that is. I'm going to substitute that value. I'm going to evaluate it. In this case, it's 0, so it's e to the 0 is equal to 1. Okay, this is a tool in your toolkit for evaluating these functions. It's another form of indeterminate. Okay, I'll let you finish writing that, and then we'll try other forms. Okay. All right. So we want to be able to use our limits to compare the growth of two functions. Like which one's growing more quickly, right? So as x goes to infinity, function 1 is going to infinity, function 2 is going to infinity, but which one gets there first? It's a really important question in computer algorithm design, right? Which one is more optimal? Which one's quicker? Okay, so I need to know as I'm doing some kind of a sort routine, I can evaluate this routine has a certain algorithm. It's, you know, it's going to process things, you know, with this kind of, you know, function, right? It'll go as fast as, you know, n, or it'll go as fast as n squared or log n or whatever. And then this function here will go as fast as n cubed or whatever. And I need to be able to compare the relative speeds of these two because I want to take the one that's quicker, right? I want my search engine to go really quickly. So I can take, let's just write this down. So two computer algorithms. Like say we can do like quick sort and bubble sort. These things are common to check out. Bubble sort to sort a list of size n, right? Where n can actually be really big, right? So say quick sort, they figured out was n ln of n. Like that's how long it takes to actually process a list. It's like a list of things that has like n quantities in it. Bubble sort goes at a speed of n squared. Okay, so people spend some time measuring these things, right? So now, this is like saying, which function hits infinity first, right? It's important. I want to know, right? Which one's quicker? Okay. So I can set up, I'm going to convert these into functions of x to make them continuous. N tends to be a discrete number, so it tends to be an integer. We want this to be continuous. We're going to model it using a continuous function so we can take derivatives and other stuff. So I'm going to say f of x is x ln of x, right? So I substitute in x for n. And I'll say g of x is equal to x squared. And I want to compare these two functions, right? So as x goes to infinity, we'll say the limit as x goes to infinity of f of x over g of x. So how I decide, right, which function I put in the numerator or the denominator is arbitrary, right? Maybe I'll go alphabetically, I don't know. But I have to know, based on the result that I get from the limit, what that's telling me about which function is going faster, okay? So as x goes to infinity, f of x over g of x, if that equals infinity, that means that my f of x function grows faster, right? Because f of x is going to infinity. And it's hitting infinity first, so my numerator is going to dominate. Let's say, for example, I wrote it like g of x all over f of x, but f of x is growing faster. That means this limit is going to evaluate to 0, right? Because f of x grows faster. All we're trying to say here is have some idea in your mind what your results, right? What your results are going to mean, right? So if f of x grows faster, then f of x over g of x is going to be infinity. If g of x over f of x, then it's going to be 0 because f of x is growing faster. So have it in your mind, like what you think the results are going to mean, so that when you do it, you're not like, what am I looking at here? All right, so let's write out our theorem, because now we're going to talk about doing L'Hopital's as x goes to infinity as opposed to as x goes to some number. Okay, so L'Hopital's rule for limits at infinity is what we're looking at. Can you guys all see that? It looks like it's cutting off a little bit. Is that better? I don't know why it keeps cutting out. Hang on. There, does that help? It's cutting off the edge of my page. Yeah, that should help. Okay, L'Hopital's rule for limits at infinity. Okay, so there's some words. I'm gonna write it like words in math. I'm gonna write it down. We're gonna talk about what it means. So we're gonna assume that our functions f of x and g of x are differentiable. Okay, on some interval b to infinity. Okay, so before we always said a to b, some open interval, but now we're specifying for sure that this interval includes infinity. Okay, so b to infinity, and that g prime of x does not equal to 0 for x greater than b. So within this interval, right, we don't want our denominator function to introduce a domain restriction. So we don't want our denominator to be equal to 0. So if the limit as x goes to infinity of f of x and the limit as x goes to infinity of g of x exist and either both are equal to 0, right? So f limit as it goes to infinity is equal to 0, and g of x as x goes to infinity is equal to 0, which means I'm going to get a 0 over 0. It's indeterminate, or both are equal to infinity, which technically means, you know, it doesn't exist, right? But basically what we're saying is we're setting up, it's an indeterminate form. It's 0 over 0, or it's infinity over infinity. So we have 0 over 0 or infinity over infinity. These are indeterminate. Okay, we need to have an indeterminate form in order to use L'Hopital's rule, otherwise we're using it incorrectly, right? So that means I can do this. Then the limit as x goes to infinity of f of x over g of x equals the limit as x goes to infinity of f prime of x all over g prime of x. Okay. Okay, and this is also true as x goes to minus infinity. So we did positive infinity, but we also mean negative infinity too. Okay, so we're making sure that we're dealing with an indeterminate form. Okay, if it's indeterminate, then I can use L'Hopital's rule. And instead of having x go to some value, okay, I'm having x go to infinity or minus infinity. Okay. You guys finish writing that, and we'll do example number 9. Okay, so example number 9, we need to check, we want to check, this is like what we were doing before, our examples. F of x equals x squared, g of x equals x ln of x, which function grows faster as x goes to infinity? So which function gets to infinity first is what we're trying to say. Okay, so what we want to do is individually, right? So the limit as x goes to infinity of f of x, that's equal to infinity, right? It's going to infinity. And then the limit as x goes to infinity of g of x, that's also equal to infinity. So if I put one over the other, so they're both going to infinity, right? So here's my x squared, and then here's my x ln of x. Looks something like that, right? So they're both going to infinity as x heads off to infinity. So now what we want to know is the limit as x goes to infinity. This is our indeterminate form. So L'Hopital's can be applied, right? So L'Hopital's going to be applied. So let's set it up. So I'm going to go the limit as x goes to infinity of arbitrarily I chose f of x to be the numerator, g of x to be the denominator. You can do whichever one you want. Just remember, like I said before, that you recognize what your answer is and what that's going to mean. X ln of x. Okay, so this is what I'm dealing with. So this is infinity over infinity. That's how we can use L'Hopital's. So first off, before I do L'Hopital's, I'm going to simplify. I'm simplifying because otherwise I'd have to do L'Hopital's twice. I'll end up at the same spot, but simplifying is going to help. So I'm going to go the limit as x goes to infinity, so I can cancel off one of these x's. Right, so I'm looking at, I'm going to get x over ln of x, right? So it's still indeterminate, right? This is infinity over infinity. So I can keep working it. All right, so my L'Hopital's limit as x goes to infinity. I'm going to take the derivative of the numerator, that's equal to 1. The derivative of the denominator, 1 over x. 1 over x is equal to x. As this goes to infinity, that means I'm dealing with, I get an answer of infinity, but what does that tell me? Because my question was, which function, f of x or g of x, is going to get there first, right? So because this is infinity, I need to interpret my answer. This means that my numerator dominates. Okay, which means that my f of x gets to infinity first. It's faster than g of x. Okay. F of x, we can write that out too. So f of x, so x squared is a faster algorithm, then x ln of x. Okay, so that's how we solved it. There's example 10. It's a lot like example 9. What I'm going to do is I'm going to write it out. Okay, I'll write out the example offline, and then I'll scan it in so you guys have it to look at. It's the same type of problem as this here. Okay. Any other questions, you guys? This is 3.5. We're going to start on Monday, chapter 4.1. Now, chapter 4 in our differential book is the same as our chapter 1 in our integral calculus book. I think actually 4.2 and chapter 1.1 in the integral calculus book, those overlap. Okay, so make sure that you have that integral calc book on hand if you haven't gotten it already. You're going to need it next semester anyway when you take Calc 2. Okay. Any other questions on the homework? Otherwise, I'll just sign off and then let you guys go prepare for the quiz. No? Okay. Have a great day, guys, and have a good weekend.
Thank you.
Bye.
Thank you.
Thank you.
Bye.
Thank you.
Bye. Take care.